Hey guys, I'm back. So today I'm going to be doing kicking off a video series. Okay, so this video series is going to be about getting an analog value from a digital microcontroller or a digital system. Okay, so first off, I'm going to explain. Like, you can use an Arduino, you could use a 555 timer, but let me explain what my method is. So first off, there's a few methods you could go here. You could go to get from your microcontroller. You could either use an external DAC if your microcontroller has one. You could use an external DAC and buy one and communicate to it over like I2C or SPI. You could use an R2R ladder, or you could use a PWM signal and a low-pass filter. So the reason I didn't choose an internal DAC is because none of my microcontrollers have them, so I can't use it. I didn't choose an external DAC because I don't have any, and I'm too lazy to buy them, and they cost too much. The rest of the options are much cheaper. Although, if you have the money, an external DAC is probably the best option, unless your microcontroller has an internal DAC. So that leaves us with R2R ladder and PWM and low-pass filters. Now, both of these options are pretty close in terms of cost, but in terms of simplicity, an R2R ladder is a bit more complex, and it also in parts it requires a lot more resistors. Now, obviously, resistors are cheap, but also there's no perfect halves in the E12 range. You know, the closest thing you have to a half is like 2.2 and 1, or 8.2 and 4.7, or 8.2 and 3.9. So, you know, your values aren't going to be exact because of that. And it takes up too many data lines on your microcontroller. So for that reason, I chose PWM and a low-pass filter. Okay, so what I'm going to do here is, this is sort of the broad system diagram of how this might work. Okay, so you have your microcontroller's signal output here. You can see why I chose it, because it only takes one signal out, and you can bit bang out a PWM, so you don't even need to have a hardware PWM embedded. So then you have your PWM signal here, right? You know, maybe you have something like this, like a 20% duty cycle, right? So I'm going to be assuming you guys are familiar with PWM for this, and you're going to have a low-pass filter, so just a simple RC filter. For this video, at least, we're going to get into more complex concepts of RC filters in later videos. Okay, so more complex concepts in later videos. But for now, we're just going to be assuming the basic RC filter. So your output, what you're going to do is you're going to buffer it with an op amp, because of reasons I'm going to explain later. So first off, what is an RC filter? Well, you've probably heard of RC, LRC, and stuff like that. Those letters just denote what the filter is made of. So R for resistor, C for capacitor. So that's what that is. Second off, what does low pass mean? Because I've been talking about an RC low pass filter on this PWM signal. So a low pass filter essentially means that it blocks high frequencies. So a low pass filter is a high block filter. Okay, so it's going to block high frequencies. So this low-pass filter, if you're familiar with them, if not, they have this thing called a cutoff frequency. Okay, so in an ideal world, your cutoff frequency, there'd be no attenuation on the signal, right? So this is assume your signal. You're going to have on a graph here signal level here versus frequency. Okay, so versus hertz, and then at your cutoff frequency, you would get 0. So this would be 100%. And this would be 0% down here. Okay, and right at your cutoff frequency, you would you would immediately attenuate 100% attenuation, meaning you get no signal level left. Now, this is not the way real low-pass filters work. Okay, our goal in designing our low-pass filter basically we want the simplest, cheapest, easiest to build, so I don't have to do as much explaining, and so you guys can build up more low-pass filters more easily. Okay, in the real world, we're going to have a little tiny bit of attenuation, because the resistor is going to do a bit of attenuation, and then we're going to get a curve down, and then right here, just at the start of our curve, bad focus. Okay, my camera doesn't want to focus. So just at the start, just after the start of our curve, like right here, this is going to be our cutoff frequency, denoted by F cutoff. Okay? So this means that above our cutoff frequency, we're still going to attenuate the signal a little bit. Okay? Just not very much. Then after our cutoff frequency, slowly and pretty linearly, we're going to start attenuating it, and it's going to get real close to zero. But it's never going to actually 100% attenuate anything because, there's no such thing as a perfect thing in electronics. So this means that a higher frequency of our PWM will still make it through. Say, our PWM frequency could be right here. It'll get mostly attenuated, but it won't pass through. So this is the problems with a low-pass filter that we're going to try to be correcting, is this curve is not very sharp. It's a curve, okay? So that's the cutoff frequency of a low-pass filter. Now, so let me explain the way like a low-pass filter sort of works. What is a low-pass filter? How does it work? What does it do when it works? Well, it essentially, like I said, lets the low frequencies pass and attenuates the high frequencies. So something like this, yeah, that's going to pass. Something like this, it's going to get attenuated. So this, out of the low-pass filter, that's going to pass pretty much. It's a bypass. I mean, it's going to be above the cutoff frequency. So it's going to pass relatively unattenuated. But something like this will not pass, and it'll get attenuated to a much smaller signal, okay? So what you would expect if in a perfect world with this frequency response would be this to get attenuated to nothing, and this to not be attenuated at all. Now, in reality, this is going to be attenuated a little bit, like I said, because the cutoff frequency is slightly down on the curve, and this is going to get attenuated a lot, but not 100% attenuation. Okay, so that's our problems with a low-pass filter. Now, we're going to try to combat this in our design, but for now, we're just going to go with the simplest low-pass filter. Now, there's a few problems when designing a low-pass filter that you're going to have to take into account with your microcontroller. I've solved one of them with the op-amp here. Okay, so basically the problem is, since this is a passive filter, this op-amp sort of makes it active, but the filter itself is just that, okay? Since this is a passive filter, it's going to be influenced by any resistances, extra inductances, extra capacitances that are anywhere on our filter. So we like a resistor on the input, that's going to influence it. A resistor on the output, that's going to influence it. So we really want, I mean, obviously there's going to be stray resistance and capacitance, whatever we do. But we really want to eliminate this as much as possible. So for our microcontroller, make sure that you have it set to like an output function, or if you're using something else, not a microcontroller, like a 555, make sure you buffer the input signal so that there's no resistance. So what you may need to do is get an op-amp and set it up like a buffer. Okay, so it's also going to, so this buffer here is going to make sure that there's no resistances on your input, ghost resistances or something due to your microcontroller that are like, right here, coupled to ground or coupled to VCC, because those are going to influence your filter. They're going to low down your filter and change your cutoff frequency, and that's bad. You're also going to want to buffer the output. Okay, so this is probably a more complex design than you'll see online. You're usually just going to see that. That's the simplest design, and this will work. But any loads on the output, which you're going to want to drive something, are going to influence the filter because of extra resistances, capacitances, and inductances, etc. So you're going to want to buffer the output. So this means that you have the op-amp driving the circuit, not the filter, so your cutoff frequency is going to remain the same. So this is sort of a basic design. So you drive the input so there's no extra resistances on the input from your power supply, capacitances from your power supply or whatever, and on the output so that your load resistance and load current doesn't load down the filter and change its cutoff frequency. So that's really going to be the basic design of our low-pass filter that we're going to build today for the first part of the series. This filter is going to keep getting better and better, and we're going to keep making the curve sharper and sharper. You remember this curve up here? We're going to keep making that more like this until we get a smooth analog value out of the PWM. Okay? So also for this filter, so I've sort of explained the operation here, but I haven't done a perfect job. Okay? So if you have a super high frequency, say we have something like an AM modulation, okay? So we have a high frequency making a low frequency waveform, okay? What the low-pass filter is going to do is it's going to attenuate this high-frequency signal, pardon the bad drawing, and it's going to let the low frequency pass. So we're basically going to let the low frequency pass. Okay, so you're going to get something like that on the output. Okay, so what effectively this is we're taking the average, okay, because think the average of this signal is without the high-frequency overlay. So same thing with PWM. These two are going to be basically analogous to each other, okay? You can think of it this way. I know it's easier to visualize this way. Is this sort of AM modulation, and then taking the low frequency out of it. PWM can be a bit difficult to understand, but it's going to be like this, okay? So we're going to have a short duty cycle. You know, keep in mind the frequency would get longer, and we start to have a longer duty cycle. I'm going to be doing the same thing over here and here, and then it starts to get shorter again, okay? So pardon the bad drawing, but so low-pass filter is sort of taking the average. So I know you say there's no low frequency here, right? This is just a high-frequency square wave. So we're going to take the average of this PWM value, and so the average is going to be this, okay? So we're passing a low frequency. Now you're saying, where is the low frequency? Well, it's the same thing as this sort of AM modulated signal over here. The low frequency is this wave, and the low frequency is this, because if you notice, the average value goes up and up and up and up, and then down and down and down. Okay, so that's essentially what a low-pass filter is. It's an average, because the average of this is going to be this. Okay, the average of this is going to be this. This meaning the square wave. So you can think of these two things as being equal. Okay, so a low-pass filter is going to do the same thing to our PWM signal, like this, that it would do to like an AM modulated signal. Okay, so you can think of them as low-pass filter being functionally similar, doing the same thing. So if it helps you visualize the way our low-pass filter is going to create an analog value from this digital signal here. Okay, so we now know our design of our low-pass filter, at least for now. We know our basic considerations of our low-pass filter. We know what might change our low-pass filter, capacitances, resistances, inductances on the inputs and outputs. We'll load it down. So we know our basic design, and we know how it works. It takes the average, and the average is the same as a low pass, okay? So, you know, just think about it like this. Like I said, how the average and low pass are the same thing, okay? Okay, so now what is this cutoff frequency thing that I've been talking about? Well, cutoff frequency is sort of an interesting thing. It's the point, like I said, where the high frequencies... Okay, so talking in terms of cutoff frequency, not only is cutoff frequency the frequency where, like, say our cutoff frequency is 30 hertz, if you feed in a frequency, assuming a perfect, frequency response like this, and this line happens right at your cutoff, that's a perfect frequency response of a low-pass filter. So assuming this, say this is 30 hertz, once your frequency is above 30 hertz, it's gone, completely attenuated. Obviously, real filters are more like this. But in either case, your frequency gets attenuated past 30 hertz. Now, what that also means is that if we have our square wave, again, right, our PWM signal, and I'm going to try to draw this as best I can, but, just draw it enough so that you get the idea, okay? So this would be like this. Okay, right? If this frequency, the average of our PWM signal, because remember low-pass filters average, I want to stress that a lot. This frequency of the average can't also be above 30 hertz, because if this, say this PWM frequency is 500 hertz, okay? And this frequency that we're averaging, okay, so we're creating a sine wave with the averages of the PWM wave, and this is 50 hertz, well, both of them are going to get attenuated, okay? So it attenuates any frequency, even even this frequency, which is the low-pass filter of this frequency, it can filter out the filter signal as well. So you just got to be wary of that, that even this lower frequency thing, the cutoff, it's going to still be affected by the cutoff frequency. So if this was 50 hertz and the cutoff frequency was 30, it might get reduced in amplitude like that a little bit, and this signal will get reduced to mostly nothing with our design. Very little bit of its original amplitude. So now how do we calculate this low-pass filter? So we have a low-pass filter, right? We know this. So it consists of a resistor, a capacitor to ground, and an op-amp at either side to buffer our signal so that we don't get any load from the input or the output influencing our filter. Okay, so this is our basic design here. Obviously, you could go with just this, but then loads on your output are going to influence your filter. So how do you calculate the cutoff frequency? Because that's the property of our filter that we're interested in designing. We want to make it so that we cut off a square wave and we leave out the resulting output, which could be pure DC in somewhere in the middle. We basically want to be able to leave the average. So how do we calculate this cutoff frequency? Well, the cutoff frequency, okay, is equal to 1 over 2. Oops, I'm sort of writing sideways relative to the camera here. 2 pi RC, okay? 1 over 2 pi times the resistance times the capacitance, okay? And these resistances and capacitances are in just regular farads. So millifarad, which is 1,000 microfarads, is going to be, so we'll go 1 microfarad, because that's a pretty standard value, would be equal to 0.000001 farads. Okay, so just keep that in mind, that this capacitance is in farads. And the resistance is obviously in ohms, okay? So now comes the tricky part. We want to determine our cutoff frequency for this filter, okay? And I want to, I'm going to use an Arduino, because that's what I like to use. You could use anything, and then your design for the cutoff frequency will be a bit different. But I'm going to use an Arduino. Now, I happen to know that according to arduino.cc, which is the Arduino website, that the Arduino's PWM signal happens at 490 hertz. Now, when I first looked at that, it seemed very low, but I measured it on my scope. You can see right here a picture, or a small video clip, actually. And it is indeed 500-ish hertz, okay? So, I mean, that's very low. That's unnaturally low for a PWM signal. So that's going to make our job a bit tougher, but it's going to mean that I'm going to have to design better low-pass filters. So this probably won't cut it, but we'll see, okay? So we know that on our output, that the higher frequency, in this case 500 hertz, 490, we'll round it up to 500 just because we like even numbers in electronics. So this frequency, we know we want this to be completely attenuated. We want this to be gone. The only thing we want left would be this thing. But we don't want this to be gone. So we have to realize what is the highest frequency signal that we want to be able to generate with our PWM. So not only do we want to be able to generate pure DC values at any one of the 255 steps in the PWM, right? But we also want to be able to generate some basic signals of some low frequencies. Okay, so maybe we want a low frequency sine wave. So I'm going to say I want some 10 hertz signals. Okay, so I want to be able to use this PWM to make 10 hertz. So that means we're going to have to pass 10 hertz. Okay, so we want a 10 hertz pass. Now keep in mind that, like I showed up here, this would be a perfect response, and this is a real world response, okay? Like this. Now our goal in designing this filter is to make this response as sharp as possible. But for this design here, this is going to be roughly our response. And so this is the cutoff frequency here, okay? Would be this vertical line. And so you notice that, like I said before, the frequencies are going to get attenuated slightly above the cutoff frequency. So if we put 10 hertz as our cutoff frequency, sure, the 10 hertz average will still get through, and the 500 hertz PWM signal will be mostly filtered out. But the 10 hertz signal, all the way through like a 5 hertz signal, will be attenuated some. And that's not good, because we want to make precise analog values here. So we want to have our cutoff frequency be more like, we want our 10 hertz, to fall more like here. Okay? So we can set our cutoff frequency. We're going to have to set it higher than 10 hertz to account for this. Now keep in mind, this is a trade-off. The higher you set it, the more of this PWM frequency that's going to get through. And the lower you set it, the more you're going to attenuate your low frequency signals that you're getting out of the PWM, and you may not have the precise analog value that you want. So there's a little trade-off here. In my case, for the cutoff frequency, I'm going to select 50 hertz because it's a multiple of 500 and it's a nice, neat value. Okay, but you could select anything you want. So I'm going to show you what to do once you've selected your cutoff frequency. So this is going to work for anybody. Okay, so our cutoff frequency, we know it's 50 hertz. So we're going to write 50 over here equals to 1 over 2 pi RC. Okay? So if you know your basic algebra, you know that you can't possibly solve for two variables. Okay? You need one of these variables. You need to pick a value for it. Okay? So we're going to have to pick either a value for our resistor or our capacitor. Now, in my case, what I'm going to do, and you can do differently, but I find it's nice for me to pick a capacitor first. And why is that? It's because it's much easier to make resistor values, and there are many more standard resistor values than there are standard capacitor values. Okay, so we're going to pick a capacitor. And in this case, since lower frequencies are usually lower capacitance, higher frequencies usually higher capacitance, you can go by that rule of thumb. So from that rule of thumb, I'm selecting a 1 microfarad cap. Why 1 microfarad? Because 1's a nice even value, and it's relatively a high capacitance in the scheme of things. Okay, if this was charged to many kilovolts, this might kill you. 1 microfarad is quite a bit of capacitance in the scheme of things. Okay, so selected this 1 microfarad cap because one, it's reasonably, like I said, reasonably large capacitance. So and the lower frequency, your cutoff frequency, obviously 50 hertz is a very low frequency. The higher value you want your cap, and the higher value your cutoff frequency, the lower value you want your cap. So that's what you do. You select your capacitor value. Okay, so now what you're going to do is you're going to rewrite the equation. 50 equals 1 over 2 pi r, and then 0.000001. And this value would obviously be whatever cutoff frequency you wanted, so put this into your own design, and this would be whatever capacitor you chose, okay? So you can put that into your own design. And then I won't do the math on camera, but I'll come back and then show you the finished product, and maybe help you get through the equation if you find it difficult. Okay, so I've done the math here, and as you can see, this is where I got, I just wrote 1 as 1 micro instead. I wrote the 1 microfarad is just 1 micro, just to simplify it up. But essentially what you have here is you have your cutoff frequency, 1 over 2 pi, the resistance, and the capacitance you've chosen. Okay? Then you can multiply by 2 pi the capacitance, so, and then on this side, you would logically get 100 pi times the capacitance, which is 1 micro. Okay, so 100 pi times 0.00001 is equal to 1 over r, and then you can just switch that with r if you know your basic algebra, and you get 1 over 100 pi 0.00001, and that gives us 3.183 K, roughly. Okay, so now what we're going to do is, well, 3.183, that's sort of a non-standard value. Okay, so what we're instead going to do is we're going to take a more standard value like 3.3. Okay, 3.3 is a very standard value. So this is a 3.3K. So we're going to use a 3.3K because that's the closest standard value to the value that we picked. So now we know our cutoff frequency because 3.183 and 3.3K are going to be a bit different. Okay, so we know our cutoff frequency isn't going to be exactly 50 hertz, but we also know that this resistor has a 5% tolerance. Okay, so what we're going to do now is we're going to calculate our actual cutoff frequency for this filter. So I'm going to zoom in on the multimeter here, and it's going to measure the resistance, 3.27. Okay, so we're really doing 3.27. So now I'm going to re-go through the formula and calculate, obviously, I'll leave you guys to do this, is when you make your own, choose your capacitor, and measure the capacitor, and then put the actual measured value. I didn't do that in this case, but put the actual measured value into the formula, find the resistor, find the closest standard E12 or E24 value of your resistor, and then re-go through the formula and calculate it to make sure it's close enough. If it's not close enough, you may need to buy some precision resistors or use series and parallel or use a trim pot or something. But in this case, I'm going to say the closest standard value to 3.183K is good enough for me. Okay? So now what we're going to do here is we're going to get out the breadboard and build this up. So here's the breadboard and ready. This is how easy it is to build one of these things. Okay? I'm going to take my resistor, bend it over, and ready? I just built it. Okay, I haven't built up the op-amp part yet, but I built up just the RC filter. Okay, so this RC filter is all we need to actually filter. Now, the op-amps, I'm going to put those in later, but right now I just want to show you. This is the RC filter. This is all you need. It's called RC, resistor capacitor, like I talked about. So now what we're going to do is I'm going to put in the buffers. Okay, I'm not going to show you how to do that. You can do that on your own with some op-amps. I'm just going to use an LM324. Not super high bandwidth, but again, we are working with very low frequencies. And then what I'm going to do is we're going to measure this filter. We're going to see how effective it is at changing PWM to an analog value, and we're going to investigate some of the characteristics of its frequency response. Okay, so I've built it up here on the breadboard, and I'm going to try to explain what I'm seeing here on the scope in a second, but just as you can see, I've got the op-amp hooked up here. And there's a few things that you need to realize. One, this is the LM324, so it has issues with the fact that it can't meet its supply rail. Okay, so it can't get all the way up to 5 volts. So that means you can't power it from the Arduino. I have it powered with this separate supply here at 10 volts. But if you can see here, I'll show you that on the scope in a second. So we have the input hooked up to a buffer. The buffer's output goes to this part of the resistor. We're taking the signal from this part, buffering it, sending it off to the scope, okay? And on the scope, they're both set to AC couple and to 1 volt per division, and I'm using times 10 probes. So you can see the original signal is 1, 2, 3, 4, 5, just about 5 volts, 5 volt square wave, okay? And it's about 50% duty cycle. And keep in mind the second signal is AC coupled. If we ground couple, oh sorry, that's the first one. If we ground couple it and put it here at the bottom and DC couple it, you notice it's going to be in the middle because of our goal is to get a voltage in the middle basically. So this signal would be in the middle. Okay, but there's a few things that you're going to notice. Actually, I'm going to set that to DC couple to notice. One of the first things is that, probably can see that better, is that we have about a volt of ripple on our signal, okay? I'm going to AC couple it there. We have about a volt peak to peak of ripple on our signal. And this is definitely a lot better, and this volt of ripple happens at the precise DC spot of our signal about there, so that's good. But the problem is this is a whole volt of ripple, so this is pretty much unacceptable. Okay, so this ripple is precisely the problem that we're going to fix in our next design of this filter. But in this current design, you could get roughly a 10 hertz signal, just like I described earlier, through, one sec, let me flip to the page, through a method like this, okay? If you remember that, remember the sort of AM modulation type thing and this are the same thing. So your frequency, not your PWM frequency, but you could actually make a sine wave out on this thing that was about 10 hertz. After that, it would start to attenuate down that signal as well as the PWM frequency. Okay, and you could do that for this. And using this method, you could create an analog value that's anywhere you like. Okay, obviously, if you didn't need the 10 hertz on the output, you could increase the capacitance to decrease the cutoff frequency of your filter. For example, if you take note, I'm going to put another 1 microfarad capacitor in parallel, which will give us twice the capacitance. So you see twice the capacitance, and I'm going to turn up the volts per division on the second one. And okay, and now if we put in the capacitor, if we take out the capacitor, put in the capacitor, out, in, out. So you can see that increasing the capacitance, switch that down to be the same again, increasing the capacitance will decrease the cutoff frequency of your RC filter, and that means it'll more effectively cut off this ripple here. Okay, but since I want more than just DC signals, I actually want to be able to make a 10 hertz signal. We're going to have to edit this this filter design of this thing that we have right here. Okay, we're going to have to improve this to improve our ripple. Okay, so that's going to be the what the rest of the series is about, basically, is decreasing our ripple so we can get the 10 hertz frequency out and have a pure, nice, clean DC waveform. Okay, so thanks for watching, and we'll see you in part 2. Just, but before I go, one quick thing: the scope ground, since we're using 2 channels, this is just a quick scope hint. Only one ground has to be connected because both grounds are connected. But remember for this, the LM324. Also, this supply rail issue, if we set this to be DC coupled, and I'm going to tune down the voltage, you can see the actual voltage that we're getting between goes down when I lower the voltage down to like 5 volts. And then between 10 and 15 it's the same, and I lower it down to 5, and it starts to drop, okay? So if you don't put like a 10 volts on your LM324's output, you could get that issue. So remember, you can't just use the 5 volts of the Arduino. You have to use a separate power supply for this design. So that is one of its limitations. But you can experiment, because everything will load down an RC filter, but the loading may be so insignificant that it doesn't matter in your case. So you may try without the buffers if you can't get a high enough supply voltage. So thanks for watching.